Hi, I'm Emily Wong from emilylearning.com. In this video, I'll be sharing with you what you need to know on electromagnetism. Before I go on to our topic, I would like to share with you some of the resources that I've created recently. So one of it is the O-level physics formula. So in this blog article, I go through or I list down all the physics formulas that you need to learn from each topic. Okay, I've also provided a list of physics definitions here. So you'll find all the common definitions that you need to know for your O-level physics exams. And you can find them at this link here. So I provide the link in the description below. I also provide individual links for this blog post on the O-level physics formula and the O-level physics definitions. Okay, so now let's go back to our topic. Alright, so let's take a look at the syllabus to look at what is tested on the topic of electromagnetism. So in the first part, we will be looking at the magnetic effect of a current. So under the magnetic effect of the current, in part A, you need to be able to draw the pattern of a magnetic field due to currents in a straight wire and its solenoids and state the effect on the magnetic field of changing the magnitude and or direction of the current. So in short, right, what you need to know is if there is a current flowing through a wire, there will be magnetic fields generated around it. Okay, and you need to be able to draw the pattern of the magnetic field generated. Okay, so for your syllabus, basically you need to be able to draw the magnetic field lines through a straight wire as well as through solenoid. So if it's a straight wire, so this is a piece of paper and I have a wire. Okay, let's assume the direction of the current is going upwards. Okay, so the magnetic field will be concentric circles. Okay, something like this. Okay, so yeah, and to find the direction of the magnetic field, what I need you to do is to use your thumb. Okay, so use your right hand. You need to use the right hand grip rule. Okay, so your thumb of your right hand should be pointed upwards. Okay, because the current is moving upwards. So the thumb of your right hand points to the direction of the current. Okay, then take a look at your fingers. All right. So so for example, these are my fingers. Pardon my poor drawing. Okay, so I noticed that my fingers are pointed in this direction, right, of my right hand. Okay, so I know the direction of the magnetic field will be in this here way. Okay, so this will be the direction of the magnetic field generated. Okay, similarly, if I have a wire, okay, and the current is going downwards, okay, the current is moving downwards. Okay, so I know that if I have a straight wire, okay, the magnetic field pattern will be concentric circles. So I'll just draw circles here. Okay, so these are the circles. Next, I need to find the direction of the magnetic field. So I use my right hand grip rule. So the thumb of my right hand should be pointing downwards, right? Because the current is flowing down. Okay, so if you were to take a look at your fingers now, okay, pardon, so this is my thumb. Okay, this is my thumb, it points downwards. Okay, then my fingers, they are in this direction, right? Okay, so in other words, right, the direction of the magnetic field or the arrows of the magnetic field will be pointing in a clockwise direction. All right, next, you need to be able to draw the magnetic field through a solenoid. Okay, so now let's assume I have a piece of paper, okay, and I have a solenoid. All right, okay, okay, so oops. Okay, so there's a current going down. Where it's going down? Where's oops? Maybe let me draw it again. Okay, so I have a solenoid. Okay, so it goes upwards. Okay, it can this way, right? Okay. So for example, there should be a resistor here. Okay, so my current is going to go this way, right? So this is the front part, so it comes down. Then comes this the front part down, front part down. Okay, so to find, so this I know that for solenoid the magnetic field lines will look like this. Okay, a straight line here, straight line here, straight line here. Okay, then I need direction of the magnetic field lines. So I need to use my right hand grip rule. So now my fingers should be pointing this way. So because the current is moving this way, my fingers of my right hand should be in this manner. Okay, then take a look at your thumb. Your right hand's thumb will be pointing in this direction. So in other words, right, your magnetic field should also point in this direction. Okay. All right, so do practice drawing the magnetic field. Okay, so take a look at your textbook. Look at how to draw the magnetic field lines for a straight wire as well as for a solenoid. Okay, then you also need to be able to state the effect on the magnetic field of the changing the magnitude of the current. So when the magnitude of the current increases, the magnetic field line should be closer to each other because the magnetic strength increases, right? When the direction of the current is reversed, take a look at this. What happens? The magnetic field, the direction of the magnetic field is also reversed. For more details on how to draw the magnetic field lines through a solenoid as well as through straight wires, do check out my Udemy course on magnetism, electromagnetism, and electromagnetic induction. Alright, next you need to be able to describe the application of the magnetic effect of a current in a circuit breaker. So let me draw a simplified diagram of a circuit breaker. So there is a soft iron core here, so to act as a temporary magnet. And you have so this is the live wire. So this is a solenoid, okay, which is connected to okay, to this contact here. So I have this contact here. Okay, and it's connected to a spring, meaning this is free to move about and maybe it's pivoted at this position here. So I draw this circle, it's called the pivot. Okay, and it is in contact with the another contact. Okay, and okay. So this is the live wire. Okay, so what it does is the electricity or the source passes through here and to this electromagnet. So this is a solenoid. So this is an electromagnet. So this is a soft iron. Remember, soft iron is easily magnetized and demagnetized, so it acts as a temporary magnet. Then the wires is then converted to connected to these two contacts. So this is free to move about. Okay. Then this portion here, it's connected to the maybe the load that you have. So for example, it goes to other appliances. Basically, it goes to another switch, okay, that you have at home. Okay, so these in between this, right, you will have your appliances and so on. Okay, so this is how a circuit breaker looks like. So the purpose of a circuit breaker is basically, right, to trip to cause a trip when the current exceeds a predetermined amount. Okay, and how does it do that? Well, okay, on normal conditions, these soft iron gets magnetized. So when there is a current flowing through, this soft iron gets magnetized. Okay, if the current is not too strong, the magnetic force or the magnetic strength of this soft iron is insufficient to attract this contact here. Okay, so if it doesn't attract this contact, these two contacts are touching each other and there will be a closed circuit. Okay, there is some appliance and so on here. So this is a closed circuit. So basically, the electricity can flow through. But once there is a large current, maybe due to a fault, this soft iron here can attract this contact here, which is also made of soft iron. And when that happens, right, this contact will look something like this now. Okay, so this contact, instead of being the blue one, it gets attracted towards this soft iron here. Now, when this moves backwards, it is no longer in contact with. So when this moves backwards, right, it is no longer in contact with this other contact. So this there is now an open circuit. Okay, so it caused the current to be tripped. Okay, so the electricity is not able to flow because you cut off the electricity. So let me erase this. So what this shows is that when the current exceeds the predetermined amount, this contact will get attracted to this soft iron because the magnetic field generated by this soft iron now becomes strong enough to attract this. Okay, and then now you have an open circuit. Okay, so the current cannot move from this contact to this contact because there is a barrier here. There's an air barrier here. So when that happens, you actually trip the circuit, and that is how the circuit breakers works. All right, now let's go on to part C. So in part C, we are asked to describe experiments to show the force on a current carrying conductor and on a beam of charged particles in a magnetic field, including the effect of reversing the current and the direction of the field. Okay, it says a lot of this, but before I go on, right, what this basically tests is, okay, so typical questions for this is I will give you maybe magnetic field. So when I put crosses, it means going into the paper. So this cross represents magnetic field going into the plane of the paper. Okay, and now I have a positively charged particles that is moving here. So what would be the direction of its motion when it enters the magnetic field? Okay, so for this type of question, what you need to do is to apply Fleming's left hand rule. Remember Fleming's left hand rule, your left hand, so you have your three fingers, right? Your thumb, your second finger, and your third finger. They should be positioned such that the three of them are at right angle to each other. Okay, so the thumb will point to the force that is acting on the charged particle. The index finger or the second finger will be pointing to the direction of the magnetic field, and the middle finger will point to the direction of the current. So since the charged particle is moving this way, right? Okay, so the middle finger should be in this direction here. Okay, so your third finger should be pointing in this direction here. Magnetic field goes into the plane of the paper, so your index finger should be pointing into the paper. And if you to look at the direction of your thumb, you'll notice that your thumb is pointing upward. So therefore, the charged particle will move in this direction once it enters the magnetic field. Okay. Part D, you need to be able to deduce the relative directions of force, field, and current when any of these two quantities are at right angle to each other using Fleming's left-hand rule. So basically, it's the application of Fleming's left-hand rule. Okay, in part E, you are expected to describe the field patterns between currents in parallel conductors and relate these to the forces which exist between the conductors. Okay, so you need to be able to describe the field patterns between currents in parallel conductors. So basically, like currents. So if the currents are moving in the same direction, they will be attracted to each other. If you have unlike current, one moving up, one moving down, they will repel each other due to the nature of the field patterns. Okay, and you need to be able to draw them. Okay, in part F, you need to be able to explain how a current carrying coil in the magnetic field experiences a turning effect, and that the effect is increased by increasing the number of turns on the coil as well as a current. So remember, in Fleming's left-hand rule, you need to use three fingers: force, magnetic field, as well as current. So in other words, right, if there is a magnetic field and also if there is a current, then there will be a force generated, and provided that the magnetic field and the current are not parallel to each other. Okay, so for your O-level syllabus, don't worry, the magnetic field and the current must definitely be perpendicular to each other. Okay, and to find the direction of the force generated, you will make use of Fleming's left-hand rule. Okay, the thumb points to the direction of motion. Okay, so basically, so what you need to know is if you have a current, so current plus magnetic field, and as long as these two are not parallel to each other, there will be a force created. Okay, and this force is dependent on the size of the current. So the greater the size of the current, the greater the magnetic force produced. And if the current is passing through a coil, okay, then the more turns there are in the coil, the greater the force produced. Okay, and you need to be able um, to apply it to the turning to that of an electric motor, to how an electric motor works. So let me draw a very simplified diagram for an electric motor. So this is an electric motor and you have a split ring commutator here. So it's basically two open circle. There's a carbon brush. Okay, let me draw a variable resistor, and it is always connected to a DC supply. Okay, so when this is connected to a DC supply, there will be electricity passing through, right? Passing through the coil. Okay, then I also need to have magnets. So let's assume this is the north pole, this is the south pole. So now I know that, okay, there's current passing through, right? So at this moment in time, I notice that there's current, right? Okay, then I have a north pole and south pole. So I have a current and I have a magnetic field generated by the magnets. So current plus magnetic field at right angle to each other, you will have the force being produced. And the direction of a force is dependent. It can be found using Fleming's left-hand rule. So if I take a look at this, right, my middle finger point in this direction. Okay, then my magnetic field is from north to south. So I'm going to point in this direction here. Okay, I'm going to point in this direction here, magnetic field. So my second finger point in this direction. So using Fleming's left-hand rule, I know that my thumb is pointing downwards. So the force exerted on this portion of the coil is downwards. Okay, and if you have to apply Fleming's left-hand rule, the direction of the force, okay, on this side will be upwards. So in other words, this coil will be turning in this direction here, which is the anti-clockwise direction. Okay, So that is how the electric motor works. You have a current passing through the coil, and you have a magnetic field just because you use magnets, right? So because the coil and the magnetic field are at an angle to each other, i.e. not parallel to each other, there will be a force that is being generated which causes this motor to turn. Okay, then you notice that there is the hole here, right? So what happens is this part of the arm is always moving upwards. Okay, when it is connected to this part of the circuit is moving upwards, right? But if this arm is always moving upwards, it will never be able to complete a cycle. Okay, it cannot turn round one round, right? Because if this is always moving up, um it is perpendicular, or once it reaches the top, it cannot go up again, right? It needs to come down. So when it reaches the top, okay, this portion, this this space here is actually in contact with the carbon brush. So so when you have a space in contact with the carbon brush, it means that you have an open circuit. And because the coil is already moving in this direction here, okay, the momentum will cause it to uh, pass the vertical and go to the other side. And once this portion pass the vertical and go to the other side, this portion of the commutator will be connected to this part here. Okay, and because it's connected to the negative terminal of the coil, the direction of the current will now be reversed, so it will start to move downwards. Okay. Okay, so this is how the electric motor works. So if you want a detailed discussion on how electric motor works, in my Udemy course, I go through in detail, as well as I also go through some of the common questions on electric motor. Okay, next you need to be able to describe the action of a split ring commutator, okay, single coil motor, and the effect of winding the coil onto a soft iron cylinder. Okay, so what you need to know is what is the purpose of a split ring commutator. Okay, so it is to allow the coil to move in a continuous cycle. Then and the effect of winding the coil onto a soft iron cylinder. So if you have a soft iron here, what it does is it concentrates the magnetic field around this coil, so therefore it will increase the magnetic force. All right. Thank you for watching this video. Do subscribe to keep updated with our latest videos. And if you are interested, we do have an entire playlist on all the topics tested in physics O level, where we share with you what is tested in detail. Okay, in addition, if you want to learn in detail, do check out our courses on Udemy. Bye and see you.